Now we have to be careful about what we say.
Gotcha.
Now we are being recorded.
Oh, yeah, don't say too much. Don't say anything.
Yeah. Is it charging? I mean, it's barely connected.
I hope
it is.
Yeah.
It feels like a charger.
Yeah, there's a charger there too.
Here as well.
Yeah,
I think if it's.
Yeah,
Oh, there it is. Yeah, I guess I can put it here.
There.
Yes, I think we could put the laptop here and, or, yeah.
Okay.
Maybe okay. Okay. Here it is. Good. All right. Yeah. Thank you for coming, everyone. Today we're very happy to have Lorenzo Ricci visiting us from Maryland, who's going to tell us some things about energy correlators. Let's take it away.
Thanks a lot. Thanks a lot for the introduction, and thanks a lot for having me here. And as I was saying at lunch, it's my personal attempt to try to find something new to do with collider, and in particular with DLAC.
Not a long introduction, right?
And and unfortunately, we are not yet there. So at least not yet phenomenologically, but at least I'll try to tell you what is the theory behind it and why it's interesting, and how we're having fun, and what are the things that we're trying to understand. And there are local experts here working on that. And that actually also said you already had a talk on energy correlator on Monday. So it's just going to be very short with the introduction. And the idea is very old and it's very simple. Usually when at least to do collider physics, we think about cross-section. So transition amplitude from initial to final state. And we're very good at computing them. And we have a lot of expertise in that. But when we go to actual experiment, we see that this definition is actually not really what we do or what we measure. Actually, what we measure is more a sort of mean expectation value, meaning that we fix the initial state, our beam, and then our initial state evolve and eventually get to some final state. We cannot do much on the final state, so we just basically sum over all possible final state, and then we measure some property of the final state. Okay, so a slightly better observable that we can choose is a sort of mean expectation value where this D that I will define in a second are detector, measuring some property of the final state. And as I said, I mean, we are very good in complete cross-section, and of course, it would be crazy to say that the right-hand side is always the best framework to do collider physics, but sometimes, for instance, in QCD, is very difficult to define cross-section, or even impossible in theories where we don't have we don't have advanced metrics, like for instance, theory that are conformal or almost conformal, and the right-hand side is slightly more convenient. Let me also point out that from the right-hand side seems a bit bizarre, because to select a final state, we really need an infinite number of detectors, which we pretty much have actually at DLAC, but at least theoretically, you see that it's a bit bizarre. Okay, so as I said, it's a very old idea that was produced basically 40 years ago or more. And the most simple detector that we can imagine measure just the total energy flux in some direction. So imagine, for instance, a plus and minus collision. We just put some detector there, and this just compute the integrated energy in this specific direction. Okay, so that's basically a mathematical definition. I integrate the stress tensor in some direction, and I very far from the center of the collision, potentially at infinity, and then I just integrate over time. And the angle just parameterize where my detector is on my detector surface. Okay. Sorry, and yeah, energy correlator just basically expectation value of energy detector, just a definition. Okay, there are many possible advantages for DLAC, and that's why I claim that it's a sort of a new topic right now. And I will not go through the details, but just three of them that I find quite interesting The first one is that you just have angles that measure, that parameterize what you're actually measuring. And angles, what they do, they basically scan different scales. Meaning that if you just collect some jet, as done, for instance, by this author, you can see that for large angles, you access to mostly the perturbative region of your amplitude, meaning that you can well describe this shape by quoting gluons, and this is the flat shape. Then when you go to smaller and smaller angle, you start scanning the different scale till you get basically 2 free hadrons for a very small angle. Okay? And there are other advantages. One of them is they are in fact safe. So in doing this calculation, you don't find any funky divergence. Then you have to cancel when you consider as better defined observable. At least this is true for, and this means, for instance, in this region here, these are precisely calculable in perturbation theory. So without relying to very complicated notation model. And there are other technical advantages, like for instance, they can be measured on tracks. And this means even experimentally, they are quite precise. And indeed, there is some first experimental attempt to measure energy correlator. As I said, in this region, for very large angle, energy correlator are quite, well described by perturbation theory. And they've been recently used to basically measure alpha strong. The idea is very simple. Here you get a line, and this line is a slope that depends on alpha strong and on the peak of the jet. So if you just fit different PT, what you're going to get are different slopes, and if you fit them, you can extract alpha strong. What I just want to point out, I will point out again at the end, is that this is basically the error on this measurement, and at the moment is already at the level of percent. Yes.
So yeah, I have a basic question, which is how do I intuitively see that different angles for different scales?
Yeah, the idea is that you start creating your core that starts showering, and basically just keep showering. If you go to small angle, you basically access to what happened at the beginning of the shower. It's a very naive way to say it, which means what happened basically at very high energy, meaning that, basically right here. When you go to small angle, what you basically focus is what happened at very late times. So when the theory is already far in infrared, so when the theory is basically close to confinement or even beyond confinement, the spheral regime. So it is that angle, they are one-to-one with time. Large angle is early time. Early time means high energy. And then, just follow the real time.
And just for curiosity,
Yeah.
sorry, they get 0.118 approximate for alpha MC with what error?
No, I forgot this. I did my bad.
No, don't worry.
Yeah, no, I should know this. I guess it was order of some percent.
10%.
Some percent, yeah. But
Some percent.
also let me say that is claimed to be at the moment the best measurement in jet substructure, not the best measurement in absolute. So it's just in the level of jet substructure, that's for sure the state of the art techniques, at least for the first round. When you go to the determination, there are other techniques. But for what, again, just to show this percent level, percent level band. Okay, and also let me say that here is perturbative, but I want to acknowledge that actually there is some recent development, actually by one of your local postdoc in the confinement regime, where perturbation theory is not valid anymore, but you can recycle other quantity that you measure a different experiment basically to try to describe this shape. So there is some development even there. Okay. We show it again. No. Oh. Now, my point is that there is a lot of effort in analytic calculation, and this is some of them. Actually, calculation are, higher order in perturbation theory, and also there are lots of new theory inside, at least a strong coupling. So I'm a bit opportunistic. I could do BSM for leading, and the way I see all of that, especially with the ILUMI approaching, is that energy correlator are a big fancy hammer, and as a BSM model builder and phenomenologist, what we should look for is basically some BSM that can be the right nail for this hammer, so that to exploit what has been done both from the theory and also from the experimental side. And this is basically the main point of my talk. And the main point is that there are basically two ways to use an energy correlator. One is basically as a new tool for all searches. And we try to make actually with some, we might be more some attempt to that, but they want to claim that, they want to say that the spirit is really by a not taken by Levi Carroll and Mesh-Gorth. And it is very simple. These are just substructural technique. We control it very well. We just have to try the best as we can at getting a precise measurement, and this we can report for BSM. There is another way on how we can use energy correlator, and we can use them as a new tool for new searches. So for searches where actually we don't have the standard techniques, and we're sort of blind on how to look for this kind of physics. And the scenario that we have in mind, and I will describe it just at the end of the talk, is basically the internal valley scenario, where we produce some BSM state that, according to some new strong dynamics, evolve in many final states, so that the dynamic is very messy. It's very hard to get track of the dynamic just by perturbative techniques. And if at the end these new states, they go back to the standard model, for instance, when the BSM is gapped, so they indicate the standard model, this will result in standard model jets just with a very complicated dynamics. And in this case, this can be a new technique to basically that we can exploit to describe this kind of object. Okay, that's basically the nail I'm looking for. But at the same time, let me say that even though a strong coupling, there are many results actually starting from quite long ago by Hoffman-Maldacena, at least in a VLDS-CFT, phenomenology requires to go beyond exact conformal invariance. And this means that there are some new theoretical challenge that we have to face, and that's basically actually the real core of my talk, and that I will try to point out. So where the theory should help, what we have to try to understand, and why this is different from what has been done. And there are two that I will try to address, or at least tell you our story. One is that the strong sector here, I'm thinking this to be very strongly coupled and to be roughly a CFT, because there is already some result. But since we're coupling this strong sector to the standard model, and the standard model, what it is, actually this strong sector is not just a CFT, but it's a deformed CFT. So some of the techniques that are used cannot be used right away, but there is some detail. So we're going to do this in RDS, just by modeling some non-trivial energy flow. I will explain this later on. And there is one other effect. The new states at the end must decay back to the standard model in order to be visible. Otherwise, this will be invisible jets, right? We know that the coupling of these guys with standard model has to be very low. Otherwise, we will see it. So that if at the end we want this guy to turn back to the standard model, we need some effect of this form. So some gap, so that the BSM at the end eventually decay to the standard model. This can be done again in ADS, but as I will try to point out, this gives some challenge. Let me also acknowledge that one of your local already made some attempt on this line. We're going to follow a different story, and so probably we'll find to resolve some discrepancy later on. But I'm going to just tell you our story, but the general message, I guess, is there. So, yeah. Okay. So that's basically the outline of my talk. Before I will just review the known result and just to explain why this energy correlator works very well as from coupling, in particular in a CFT with topographic dual. Then I will do in a way that is easily generalized to other cases. So for instance, when the CFT is not just a CFT dual to ADS, but there is some irrelevant information that we need from phenomenology, then I will tell our story what happened when there is a gap. So at the end, CFT is not a true CFT, but the state they will have a mass, minimal mass, and then I will make some comment on next linear order dynamics, and at least give you a taste of what we're trying to do applied to real phenomenology. We're not yet there, so I'm just going to give you a taste of that, but hopefully it will be interesting enough, and then I will conclude. Okay.
Just so the picture is clear to me. In your asymptotically ADS case, will it be gapped?
No, it will be just a DS, and yeah, then I will try to put the two together. But yeah, I mean, at least mathematical will not be gapped. Sure. Okay, I try to be close. Okay, are there any questions? Or anyone? Okay. So let me start actually even from a very easier model, which is basically just free particles. The idea is that we start in our collider, we just create a lot of particles, just in 4D, they just propagate, and they eventually hit the detector. So when the detector is on the trajectory of the particles, they just basically travel in straight lines. we measure the energy. As simple as that. This can be just done in second quantization, where energy correlators are just some ADAG array counting the number of particles in a given direction. I like using Fermat rules, and in this way, every time we want to compute a diagram where we have an energy correlator insertion in, an energy detector insertion in a line, what this line is doing is just taking the cut, so basically summing over a complete set of states, and then measuring the energy. Okay, so just P naught and the delta function. And the same is true when you start adding more detector. If you have more detector, they will both measure the energy in a given direction. Okay, as simple as that. Now let's go to ADS. Here, everything becomes slightly more complicated, but follow me, the logic is basically the same. The idea is that we want to model the strong dynamics just basically by an extra dimension with this metric. And it is the same. Imagine here our collision. Our collision will just spread out some particle, but the particle will just propagate through the extra dimension. Okay? And at this point, what we can do is the same as we've done before. We can ask what our detector, which is here, is going to see about this particle traveling in the extra dimension. And this is done just by taking the expectation value of the stress tensor on the classical trajectory by the particle, of the particle. So the particle will move according to some trajectory, and we just have to basically compute the expectation value of the stress tensor in this trajectory. The only subtlety is that now the particle propagates in the extra dimension, so we need to also put a propagator for our graviton, while before we were just a contact interaction. And yes, again, this stress tensor is the one of the point particle that is localized on the classical trajectory of the particle. Okay, and just here, and the energy correlator will be on the point particle with just the same. I just take the definition, so the limit for r equals to infinity, the integral over time times the stress tensor. Okay, and here just give you a couple of technical details that will be not super important, but at least want to try to be precise. And one is that in this, the theory is not gapped, so basically signal they will travel at the speed of light means that instead of integrating the detector over this slice, so very large R over T, we can just go on a light cone. Since at the end, everything will go on the light cone. And so introduce this x plus minus variable is not much important, but what is important is that we can integrate on the light cone, and we can use this unification energy detector, which is the same as before, just saying the detector now travels, is localized on a light cone. So integrate on slice at finite extent minus. And okay, the only magic is that after we do this integral over time, the location where the particle hits the detector, so the propagator detector, is localized. And it's localized in basically this place here, which is where R, which is the size of the detector, or xn plus, they're roughly the same, is equal to some component of the trajectory of the point-like particle. Now, this xn plus, which is roughly R, becomes very, very large. And it means basically that this point goes far and far and far into the bar. Okay? And yeah, so we can just go ahead, far into the bar. This particle will travel basically just a massless particle in ADS. The idea is just that ADS works like an linear accelerator. So as it moves here, it keeps accelerating, accelerating. And if we just substitute the classical trajectory, what we will see is that the classical trajectory is just the momentum times the fifth dimension. And they will interact basically here, very, very far away, basically at infinity. So there is some physics in that. So the particle is not heading to the detector a priori. If we are working on the side, it can just go direct somewhere here and the detector can be in a different direction. Yet they can meet somewhere here in the bulk because the particle can be, this fifth dimension can be as large as this interaction to happen. Okay, this was a bit technical, but this was the main point. And again, the main point is that as they go into the yard, at the end, I can get the detector. And since the detector does the measurement really at late time, it does it really in far AR. So really for the large W. Okay. And that's basically the result that you're going to get. This was a result in a BFTP. Here we're just restrained in terms of point-like particle. But the result is basically that the energy distribution that our detector will see on our detector surface will just be of this form, so that if you take P to be at rest, it's just an isotropic and dense energy distribution. Wherever you place your detector, you're going to measure something. Okay. Now, this can be done slightly more systematically in second quantization. We can write an action for our particle which becomes a field. We can decompose it in terms basically of KK modes, and we can just go ahead and compute the expectation value of the detector in these states. These two guys, they don't need to stay, at the boundary. It can be everywhere in the bag. And this is slightly more technical. Doesn't want to change. But what's happening basically is that when this point becomes very far away, propagator from here to here starts oscillating, and oscillating very fast. And in order to cancel this oscillation, what you need is that the energy coming here, the momentum coming here, is equal to the momentum coming out. So that at the end of the day, what we get is the same result as before, that can be easily expressed in terms of cutting rules. We start from some particle propagating from one point to another point, and we act with the energy detector. We can just take the cut and just multiply by some factor that measures the energy. It's really the same as free theory. It's just that now everything is slightly more complicated because this propagates through the fifth dimension, and this factor is not anymore a delta function, but it's just this factor overall. And the cutting rule here, just for completeness, is just a standard for these cutting rules. Once we write this propagator in terms of this decomposition, was actually emphasized by this author. So it's just basically the delta function at P square minus M square, which is then integrated. Okay, that's just a practical way to compute the energy detector. Now, this can be generalized to more detector, and not surprisingly, what you're going to find is that more detector, they will both measure energy, so we're going to get always the same. Now, all the delta function, they get replaced by this new interesting factor, which tells how the energy distribute. And yes, so that at the end, this is the final formula, and we're done with the review of ADS. Basically, the energy detector is just a sum of A dagger A, which now count the particle moving into the bulk. It's just that now is weighted, they are weighted by this new factor. Okay.
Why is there not another diagram where it's just one, I think you see where one graviton comes out?
Yeah, I'll comment on that later on. Thanks. Yeah, it was a bit sloppy here, just not to annoy too much the technical details, but I get that. Okay. Yeah, I mean, and the old result was just obtained when you send this point to the boundary, and then you just go and compute this expectation value in the underlying TFT, and what you get is basically the old result from Maldacena, which is again just counting the energy of free particles. Okay, and I hope that in this way at least it's clear what's going on. Now, I went here because now we can go ahead and try to ask, okay, let's start from our CFT and just add some deformation. This can be done in, again, in extra dimension. And the way this is usually done is just mapping this operator to some bulk scalar with some specific mass and with some specific boundary condition. Okay? And the story is basically the same, doesn't change much. And you can just compute what is the difference in the metric from this insertion, just solving the equation of motion classically. And what you get is that you have a new metric, which is not a ds, but it's a ds times some prefactor here. And this prefactor is such that when you go deep into the R, for very large W, basically, you go back to a ds. That's just because this deformation is irrelevant, and in deep in the R, you go back to a ds. So I've done the review before because now it should be clear that nothing really different is going to happen. And the reason is that we can just go and draw the same diagram as before. We have our point particle, which is traveling in this fifth dimension with this new funky metric. And then we can just ask what is the energy deposited on this detector here. But the interaction is happening very, very far into the bulk, where basically the metric is the same metric as before. So that if we do that, we can see that the classical trajectory of the particle is the same. Maybe here the trajectory will be different, but asymptotically it's just gonna go as impurity S. And the same will happen for the graviton interaction. That, I mean, we'll just need to solve the equation of motion, that they will be the same as pure ADS, up just to some prefactor. But it's also true that energy must be conserved, so that if I integrate my detector everywhere on my terrestrial sphere, I must get the total energy. So this prefactor can be fixed to be equal 1, and what we get is that even in this new metric, the result is exactly the same as before. So this seems quite solid, meaning that every time we have a CFT, which is the form, but only in UV, not in the AR, we're always going to get basically the same energy distribution. And I'm going to give you a picture of what's going on in a second. Okay, and yeah, similarly, everything can be done in second quantization. I'm going to skip the details, but if you do that, what you're going to get again is that you can take this diagram, and this is going to be this prefactor times some cutting rule. And this cutting rule now will be slightly more complicated because we depend on the new metric, but the prefactor in front will be exactly the same. Okay. So, yeah, sorry, I get it done at least with the final result, which is this one. One detail that I want to add, just to answer Amin, is that this is slightly technical, so you don't need to follow if you don't want, but just let me say that in principle, there are more ways through which these two detectors can interact with our particle. They can either interact directly, or they can interact in a point-like vertex, or they can actually interact the two gravitons by themselves and then propagate to the particle, okay? So one is to check that actually what these effects are doing. The first one is really the one that I was telling you before. Every detector is measuring the energy of the particle moving in the fifth dimension. So this is just the square of the single detector expectation, and is the formula that I was showing before. These two guys are in principle slightly more complicated. So now I'm not going to show the full proof, but let me at least give you a taste. For the first guy, you need the two detectors to interact with the particle in the exact position. This means that two delta function they have to be satisfied, where this guy is the position of the first detector and this guy is the position of the second detector. These positions are very far away, but they're not the same. So then, when basically we take the limits, these two delta functions can never be satisfied, and this diagram vanishes. The second diagram, the third diagram, sorry, is even more complicated. But what you can show is that, in principle, it's not zero. But once you send these two guys very, very far away with respect to the collision point, so you send your detector to infinity, it vanishes with actually quadratically 1 over x plus squared. But up to this detail, what you can show is basically these two guys vanishes. Now, the reason why I just brought it up is one to answer Amin, and the second one is because usually this is done in a completely different formality, where that work in exact CFT, where basically you can go to a frame where these two guys directly vanishes. The reason why I have to do all this story is that when we go with this new metric, there is some detail, there's this additional detail that you cannot do a conformal transformation, which is not because it will not be an isometry of ADS. So you cannot just use the standard technique, at least we didn't find out to do it. And so I had to go through basically the calculation diagram one by one. Okay. Now let's go to the second point that they wanted to raise. And the second point is the following. Now we want to include a gap. So we know that our CFT has to decay, has to be gapped, so that the states must have some minimal mass. And the easiest way to do that is just by truncating ADS at some specific position, and the impact of the position is basically the mass of the light state, roughly. Anyway, or the gap. Okay, so the metric is basically the same as before, but now there is this new constraint. And here the things get slightly more interesting, but also, yes?
On the previous slide,
Right.
Can you get a contact term for the second diagram?
This one?
Yeah.
It vanishes. That's
Even if n1 is equal to n2?
no, if anyone, no, that's not vanishes. So they're actually, I don't know what to do. So that's a prescription. We don't not put it to 0, but in principle, that one vanishes. Just for you, I say that, the way they vanish is just to take the prescription, if you send one detector to infinity first and the second detector later. Okay? And they are on a different location. That's a prescription. That seems to give the physics that we want. But yeah, in principle, it's a prescription. So, okay. Did answer?
But I was worried if there's something like you can have a delta function.
Yeah, there can be a delta function where one on the top of the other.
Right, and then
We're just putting it to 0 by end at this level. just because the leading order result was expected to be at least physically the same as in a D. I mean, by the way, the same is in a DS, in pure DS, right? If you do the calculation in this way, you might get a delta function. If you do it in the standard way, like of Malmaldasena, the delta function is not there just because you neglect it from the beginning in some sense. Okay. So but that's a very good point. Okay, so I was saying that here things get more interesting. I tried to convince you before that basically the interaction point where the detector sees the particle is very, very far into the yard. But now we are truncating the yard. So what's going on? Are they ever going to interact? And the answer to us seems that no, they are not going to interact. So something new is happening. And so let me say again, in the limit R to infinity, this guy gets very, very far from this point. And so they will never interact here, just because this point will move on the right outside the boundary of our space. And so yeah, this delta function can never be satisfied. And what's happening here, at least the way we're understanding, is the following. And it geometrically should be quite easy, is if the detector is really on the trajectory of the particle on the boundary, if time passes at some point, this guy is going to interact with the detector, okay? So this is quite clear in second quantization. The fact that if P is parallel to M, then the particle can still hit the detector. So if we go to second quantization, we can just decompose our action for our scalar in terms of justification and annihilation operator, so in this way. And then to us, we get that the energy detector, what it's doing is just counting the particle in a given direction. So that's quite interesting. We started with a theory that had a very peculiar energy distribution. We just added a small boundary, and this gives a completely different result. So we go back basically to free theory. Okay? And let me try to give a real-time picture of what's, oh yeah, that's just a technical detail. So the calculation is done for people that had done it before. It's just basically crucial to take before the integral over time and then the limit to R to infinity, limit of R to infinity. And in this limit, you can just do a certain point approximation that selects only P parallel to N, okay? And there are no other large parameter because this W now is bounded. Before there was a large parameter that was basically the fifth dimension, and so this approximation was not valid before. In this case, it's valid. And what it is just because this is the standard way how the calculation in free theory is done. Now, let me try to give at least a picture of what we are trying to see. And that's basically the picture. We start either in our CT or in our gap CT with some signal in the center of our space. And at the beginning, if P is roughly the invariant mass of the state, its size will be its Compton wavelength. Okay, so 1 over P. Then time passes, and this distribution evolves and becomes larger and larger, till at some point reach some size, which is 1 over lambda r, both on the CFT and in the gap CFT. Here, nothing can happen anymore, because this energy distribution hadronized, it becomes a single hadron, which is of this size. Okay? Instead, on the left-hand side, the distribution keeps evolving, till it gets eventually to all the detectors. So it becomes as large as basically all our detector surface and eventually touches all the detectors. So on the left-hand side, we get this distribution, which again in the left frame is basically isotropic and dense. On the right-hand side instead, this guy is basically infinitesimally small compared to the distance between where the detector are and the size of the hadron. So that at the end we go back to some delta function. Okay, this was kind of the physics that we got, and it seems to us at least was pretty interesting because you can wonder what happens in the limit where P is much, much larger than lambda r. What do you expect? The left-hand side, sorry, or the right-hand side? You expect this to be very small deformation, but at the end, what we get is a completely different distribution. Here is delta function. Here is just some isotropic smear distribution. And indeed, on the right-hand side is also even weirder, because if you think about it, when P is much, much larger than lambda r, you're basically creating a giant hadron, which is giant compared to its wavelength, but it's still a compact object. And of course, this change once we include interactions. But at least this is what we got by brute force. Let me think. Good. Okay, so long story short, basically what we get is that with confinement, we have just some stable 4-degree mode, but in the limit where the energy is much larger than the confinement scale, basically they are going to decay. And at some point, decaying, they're going to shower, produce many partons, and then they're eventually going to get to the detector, even if the central mass is not heading to the detector. Now, if the width of our state is smaller compared to the gap, we can do this numerically. And that's a closed problem that you can do with your laptop. When instead the width is much larger than the gap, so the width of this state is much larger than basically the daughter, we lose perturbative control. And what we can do, at least we meant to do, is just find an approximation. And in this case,
This is the perturbation theory in what?
well, I mean, what you need a decay, so the perturbation theory will be in the width. The width will be the expansion parameter, the width and the mass.
So you imagine this is still strongly coupled, but the width is small.
The width is large compared to the gap. So the width can be small in absolute value, but what happens is that, you cannot use anyone.
When you have perturbative control.
Yeah. Oh, there basically what you have is just classical cascade, where you produce an decay mode that decays to
They're the width is less than lambda r.
Yeah.
And but the series is still strongly coupled.
Yes, but it still is, I mean, the resonances are weakly coupled. So you have strongly coupled resonances in 4D, but they weakly interact among each other. Okay, so that's, I mean, yeah, that's basically the idea. It's like, you can talk about pions and the pions, okay, no pion because they say, okay, they keep decaying. Your hadrons, they keep decaying.
QCD is different. QCD.
Yeah, I mean, anyway, this is very similar to what happened in large QCD. Just to make a comment, if you're
the QCD, the shower part is
but
is
larger,
perturbative. I
yeah.
think
That's large in QCD. So the idea would be, going back to the first result, is that in QCD you get quark that they shower.
Yeah.
If you work in large in QCD where NN is very large, basically, you scatter the plus and minus, what you create is just a single hadron that is stable and cannot decay. Okay, that's basically the idea. Now, if you work in 1 over n in large in QCD, it can start decaying. There is a regime where instead, n is small, it's not large enough, and then you're dominated by perturbative physics, and then you can start talking about the showering. It's very similar to what happened in large QCD. But sorry, let me say it again. We use perturbation theory because we know that hadronization is not important enough, right? But if you work in large QCD and n is extremely large, at the end, whatever you produce at your collider is going to hadronize. And this means that you cannot use your perturbative calculation. Okay? Just that perturbative here means CFT, so the second line, and non-perturbative is the part below, so you have just to invert the two. I don't know if it's clear or more confusion.
Sorry, so
Yeah.
essentially you're just like, you're starting with some, and say some heavy KK mode
Yes.
or something, and just simulate it decay a bunch of times, and then just like, just numerically extract it.
Yeah, I mean, that's in the up line. In the second line, we say that we don't even know how to do this calculation.
Right, yeah.
So we're just guessing the result to be the standard one, and now I'm going to estimate corrections.
I see.
So yeah.
Is the important that the decay is always 1 to 2, or is it
No, can be whatever.
maybe 1 by?
Yeah, by the way, sorry, now in the second part, in the second point, bullet point, we don't know how to do calculation, just because our width doesn't work. The reason is that the width is much larger than the gap. So, different decay channels, they interfere among each other. And in this case, we don't know how to do calculation, but what we guess is that what you get is after the CFT result up to correction. Similar to when you say in QCD, you can use perturbation theory up to correction, that depends on the hadronization scale. And the rest of the talk, I guess I'm late, so don't know how much I will be able to say.
We also started late, so
Okay.
we just fit over.
Yeah, because I wanted to get some phenomenology. Sorry?
But sorry, so does it matter, like the initial state you start with is gonna matter, right? Like,
Yeah, here we're just assuming a scalar, just to have it
and like, is its energy like, what is its energy like compared to the KK scale?
Yeah, that's important, yeah. So here we're just saying that in this limit,
Sorry, okay, that's the point, okay.
that's the point. So, yeah, I mean, if the state is low, I mean, it's not very energetic, then I can use the narrow width approximation. If the state is very energetic, I cannot anymore. So anyway, the whole point is that at least when this guy is very large, the one that he created with respect to his Compton wavelength, so when this relation is satisfied, I expect the CFT result to roughly hold. And then I can try to estimate correction to see how they are, and then try to use them in actual phenomenology. And the way this is done, now very more technically, just similar to what actually is done in QCD. And if there is a problem, the problem is a small angle, and the reason is pretty much the one that I said before. So small angle is late time dynamics where hadronization do matter. Okay, so but a small angle with some extra tool, which is called the light ray of E. And the idea is very easy. I consider my state and the two detector. When the detector are very close each other in angles, I can replace them with a new fancy detector that just measure basically the energy square in the direction only. Plus less singular term with the angle. So and theta is the angle between the two detectors. And this is quite obvious in QCD. If you've seen this before, at least the two detectors are together. So when this is very close, basically the small angle behavior is dominated by the splitting function for our, say, quark to go to quark and gluon. And you can just do this calculation perturbatively and replace it by a new detector. And not surprisingly, the new detector, if you see this formula and you put J equal 3, it's just gonna basically count the energy square in the direction up to a coefficient. So again, if two particles that travel very close together, you want to measure the energy of the two, they are very close to each other. So you basically just count the energy squared. And the same is true in this more complicated theory. It's more complicated, so we don't even know how to compute this coefficient at the moment. But, no, sorry, this we know, later on, the orientation correction. But basically what you can do is to do no P between the two detectors and estimate what you're gonna get on the right-hand side, just based on the selection rules of your theory. And if you do that in the theory that I showed before, so where there is a gap, the gap basically transforms like a scale, so it's just a mass scale. So you can just use it like a power 1 under dilatation. And there's another quantum number, which is boost. If you boost the whole system, angle becomes closer. Like boost a jet becomes more and more narrow. And this is just a scalar, so will not change under boost. But the angle will shrink. They will transform under boost. And at the end, what they can do is just to classify basically all the selection rules that I have and try to write down an expansion, a small angle for the interpretation value. I will get a first term, which tau is just dependent on my specific spectrum, but the only interesting thing is to compare the first term with the second term when I inserted some power of the mass. So I'm just trying to estimate mass correction there. And what you see is that basically the first guy will scale like energy square, the second guy will scale like energy because they have another mass. And if I also play with the selection rule of boost, what I get is that here I have some power of the angle, here I have one less power of the angle. And the reason is just because also energy changes under boost. If I boost, energy grows. Here I have one less energy, so I need one extra angle to compensate that. And it's very intuitive. Oh. So that if I compare the second term with respect to the second term, what I get is basically that for theta, which is larger than lambda r over E, I don't expect any effect. And my original result in CFT works. For theta, which is smaller, instead, we don't really know what to do. Let me say that the same argument was applied in QCD. There you don't have all these selection rules. So while I claim tau result is pretty formally established, here is slightly more complicated. But basically, they observe the same in QCD, where they do simulation. And what you can see is that this is the perturbative regime for large angle. When you get to angles which are of order of the energy divided by the mass divided by the energy, what you start seeing is the confinement effects. So basically, you see a bending on your line. So here you can trust perturbation theory, here you cannot anymore. But the basic physics is really the same. Okay, so far what we concluded is that for angles which are larger than lambda r over E, and for energy that are much larger than the gap, basically the basic formula is the same that I showed at the beginning. And we can parameterize confinement effects via this operator expansion, where the coefficients are in general order one number, and the rest of the selection rules tell us basically when confinement effects is clean. So basically the relation. Now there are two more points that I want to emphasize. One is that this linear result is universal, but also very boring. As you can see, it doesn't tell us anything about what we're measuring. So we don't know anything about our states. We don't know anything about what's going on. And we just know that there is something that looks like a CFT, okay? And so in particular, we cannot extract any of the parameters of our quantitative BSM. And another point is that the model that we draw was very, very crude. So we take a DS and we put some boundary. This is phenomenologically not acceptable, and we should, in principle, consider more realistic stuff. And basically, this is what we then try to do. And I'm just going to talk a little bit about what we expect to see interaction, and the second part I'm going to skip it. But as I showed before, in principle, you have an operator product expansion that already tells you something about the dynamics. You see that when the two detectors are very close together, what you get is some power of angle, which depends on tau, and tau is some control number that span the spectrum of operators. So this tells some information about the spectrum. This tells some information about the theory. So the question is, can we actually at least try to get this number, tau? And we done the calculation leading order, and what we got was pretty trivial. Oh, sorry, by the way, the leading operator can just depend on the theory, but in our theory, which is just scaling DS, we'll have a very super complicated expression. It's a non-local operator, but it's basically just some double trace operator of our initial state. Wait, we need to follow the details, but the point is that they want to emphasize is that working a leading order, this scaling is not there. So you can do calculation and you get 0. But if you work an leading order, you will see the scaling. The only point, which is probably negative, is that this will be suppressed by some coupling in the bulk, so that a leading order dynamic is pretty trivial. So again, in the rest frame, it's just isotropic, and then you get first not trivial correlation only when you go to next leading order. Okay, now in my last minutes, what I want to do, and this I will just say in words that basically you can try to do some more, realistic phonological model, or work on that is basically just try to at least stabilize the infrared boundary via some mechanism. So for instance, just adding some irrelevant deformation. And we play with it at the beginning of the talk, and we saw that this was not much important. So that the main result is that a leading order at least will still basically imagine to see that in the gap CFT plus an irrelevant deformation, which is slightly more viable phenomenological model, we still basically get the gap CFT, which is equal again to the CFT for large enough angles. So the stabilization doesn't play any role. This was super technical, I know. And and just to mention that when you go to next leading order, you have slightly more interesting dynamics. And what we are trying to see is that as you scan with the angle, when you scan different angles, what you can do is really to test your dynamic in different region of the bulk. Okay, sorry, here. So at least I want to tell you now in time, right? Do I have 10 minutes? Yeah, sure. So at least I want to tell you a little bit about the kind of phenomenology that we're trying to do. This is still work in progress, so I'm not going to show any projection because I'm not confident enough of what we have, but at least I want to give you the order of magnitude of what's going on. And as I said, one of the scenarios that probably is most promising for energy correlator are the dissident valid scenario. So what you can imagine is to have some small mediator, there's some weakly coupled mediator that mediates an interaction between the standard model and some new BSM sector, which is weakly coupled, at least with the standard model, otherwise we wouldn't notice that. And this new sector is strongly coupled and indicate to many states that if the mass of the Z prime is much larger than the gap, they will eventually produce very complicated jet with a lot of energy distributed in a particular way. Now, this is a well-known scenario, and if the BSM is a dark QCD, we already know what to do. We just treat it like standard QCD. So in particular, what we can do, we can just go there and simulate numerically whatever is happening inside here, and with some dark PTA code that keep track of this dark QCD. If instead the BSM is not historically free, so it's similar to the theory that I showed before, there we don't really know what to do. And then we really need to rely on some calculation or energy correlator similar to the one that we show. And this is roughly the shape that you expect. So here what I'm doing, now bring your line one by one, is just collecting some fudget, okay, for the Z prime, which has some large PT. 800 to 1000 GV, so it's pretty boosted. And I'm plotting two lines for the two signals that correspond either to the QCD or to a not asymptotically free BSM, like the one that I did show before. And this is in contrast to the dashed line, which is the background, just for standard model Z jet. So when you replace here, instead of Z prime plus photon, just jet plus photon. Okay? And just to understand the two different shapes, the first one, the red one, pretty simple to understand. If you go in the rest frame of the Z prime, which is a singlet, it's just going to decay into a QQ bar pair, if this is sort of QCD-like, that are back-to-back, okay? So back-to-back physics is basically telling us all what we want to know, and then this quantity will eventually shower, produce pion, dark pion, or whatever that they are, and eventually turn back to the standard model. In the rest frame, we know that to measure the energy, we need the detector to be here and here because they are back to back. Now, if we boost this configuration, what we get is basically this red line, where you see that there is a huge peak. So the peak that before was in the back-to-back region now gets boosted to a position which is basically in log scale the mass of the z prime, so 100 GB, divided by the PT. And this gets mirrored by basically by this kind of effects and also whatever effect that connect the two final state. This has been studied at the moment in 4Z boson or W boson, so this isn't clearly understood, but that's basically you can simulate numerically and that's what you get. Okay, and again, the energy distribution in the rest frame is just basically a delta function, 1 plus and 1 dot n2, which means that the two have to be back to back. Become pretty different when you have a strong safety. So if you're in the frame, the only energy you have is the mass of the Z prime, and then the energy is just isotropic. Okay, so if you do that, you can just then boost it. And if you go to the new frame, to the new frame, so where the jet is produced, you basically get an almost flat distribution with just very not pronounced peak, which is given by kinematic.
Why is it still peak somehow?
I mean, just because you're boosting a little bit, right? So there is a scale which is the mass over the energy. So, I mean, you know, if you boost any sort of distribution in some direction, you boost it to infinity, at some point it's just going to be localized in a single
Go
point.
to the rest frame.
I can go in the rest frame, yes.
Yeah.
But this measurement is not done in the rest frame. I mean, in the rest frame, I agree, it's completely isotropic. Now, if you boost the rest frame to infinity, it's going to be just localized in a direction. So that's basically why you start seeing this kind of bump. Does it make sense?
Yeah, but it's the bump is not telling you too much.
No, you're not telling
Because
that
it's just the
absolutely. No, that just will be the leading channel that you will look for. You start with standard model jets, which is dash line, then you try to fit different shapes. As I said, the QCD1 is basically this kind of very peaked shape.
Maybe it's useful to compare the distribution in the rest frame.
Yeah, but then you have to boost back the standard model.
That's doable.
Yes, you can try to do it. Yes.
Yeah.
Okay. Yeah, no, I mean, I agree with you.
Okay.
I mean, or you can just go here and compute moments of that and see that it's basically flat in the rest frame. Okay, yeah.
Okay.
We're still trying to do a proper analysis, so that's why I'm, let's put it at the end of the talk. But just at least to compare what we expect, this is the background. This background is basically the same that was used for alpha strong measurement. There it was jet, here is jet photon, but it was the same. You just collect single jet and you plot 2-point energy correlation inside the jet. Okay. And what you get is basically just some flat distribution up to a scale here where confinement becomes important. Again, I'm showing you this just to say that this line here is known at percent level for any different PT. Now, if we compare this with bounds of this kind of model here, which is just a Z prime with two prong, what you can see is that the standard model coupling versus the new coupling is a percent level, which is roughly the same order of magnitude as at the moment this distribution are measured and computed. Actually computed way better than this, measured. So at least I want to show you a projection, which is still too preliminary, but the order of magnitudes of at least for the red line, which is well studied right now at Atlas and the in general of CMS, seems to be the same order of magnitude, the possible signal of basically the shape that is measured in energy correlator. Okay, so that's basically what now we are trying to do slightly more in details. And I'm gonna conclude. Read very fast, but basically energy correlator rapidly developing tool and potential sensitivity to BSM is completely unexplored. And in my opinion, inner valley are the ideal target, and that's what we're trying to do. And phenomenology at the same time required to go beyond exact conformal invariance, and this raised some theoretical question. We played with holography just because there we knew where to start, and it can be done in general, but it's more complicated. The first point was that CFT must be broken at least by renal deformation, and what we found is that at leading order, the dynamics, there are no effects at leading order, but next to leading order, there is some not trivial dynamics that can tell us what's going on inside this weird neophysics jet. There is another point that we had to go through, which is the effects of the gap. So as soon as we truncate a DS, what we got is basically that our calculation is completely unreliable. And in this case, the way we handle it is just that we assume that the CFT was given the correct distribution, and we try to estimate effects of confinement based on some theoretical argument based on the light OP. But at the same point, let me admit that we don't know how to compute any confinement effects, or including the OP coefficient that are on the confinement. So actually, we didn't solve the problem. And let me also mention that there is a different story actually by Amin and collaborator. So there might be some other way to go. And I close here.
Question for Lorenzo?
Yes.
Yeah, so I have question about the relative deformation. You're saying that are you keeping the boundary condition fixed in your relative deformation?
Yes.
But that is not actually the case, because your relative deformation could change the boundary condition, which could change the leading order behavior.
Yeah, sorry, give me 1 second. Stupid. What it is?
Yeah, that's
So this is boundary condition, right?
yeah, that's the Dirichlet case, right?
Yeah, I mean, that's what we're considering. 15 is plus some deformation.
Yes, but if you change the metric, it will in principle change the boundary condition of the graviton and also other things. So your leading order behavior might change in this case.
If you add this deformation.
Yeah,
I mean, that's what we was trying to explain. We've been careful of that. So we keep everything, we change the boundary condition, and we still keep this to be an irrelevant deformation. If it's relevant, it doesn't work. So let me be precise. And as far as the deformation is irrelevant, what we got is that we get exactly the same as pure ADS. Now, I don't know if I can. We are going to the technical point. Let me see if I can. No, can I try to do it with my hand? I mean, what we got is basically that you produce this particle, whatever it is, that it starts, spreading in size as time passes. Now, if you're in a CFT, asymptotically, this basically expands the speed of light till basically getting to all the detectors and getting this precise energy distribution that they did show, this one. Okay. Now, whatever deformation we are putting, we are very careful that the deformation doesn't change when W is very large. So at late time, you basically your state is the same as in a pure CFT or in pure ADS. I don't know if I'm being clear, but basically the main point is that the measurement is done in the deep IR. Okay, so when W is very large in this metric, but in this metric, when W is very large, we basically go back to ADS, because you see that this factor here goes to 0. Just because delta tilde is larger than 4, so this is negligible. And since we're taking this really to be infinite, in this limit, there is no effects, and we go back to ADS. At least that's morally. And if you want, we can go more technically, but that's basically the idea. Okay, but then you point out that if you change this delta tilde to be less than 4, the metric becomes important in the AR, so everything is completely destroyed, and the result is not valid anymore. So that's important. That deformation might be irrelevant if you want really to have CFT in the deep IR. Okay.
I have a question. I'm somewhat confused by the again by just like the simulated cascades of decays. Like I understand that if you're in the regime where the decay width of your bulk scalar or whatever is large compared to the KK scale, right? Then
Yes.
Then you lose narrow width.
Yeah.
So it's hard, but it's still a weakly couple. No?
Yeah, that's a good
So
point.
I should, in principle, still be able to simulate the same.
There should be a way.
I mean, I don't know how, but
That's a good point. Yeah, I mean, in principle, it should be able.
presumably, if you can do this, then you can like
Yeah, check
see
everything.
the transition. Yeah.
Yeah, that's a good point. It should be doable. We didn't know how to do it. One of the reasons is that you don't have narrow width approximation.
Right. Yeah.
So
I
every
don't know how to
time,
do it either.
every time you decay to many states, and you have to keep track of all the interferences, which seems quite complicated. What one can try to do is to start from where you know what to do, and then you start increasing, and try to get numerically at least some trend of the shape. For us, the main point is that at least in the regime we're interested in, where the width is much larger than the gap, it's okay. We are already okay with the CFT result, and we then go through to get the full confinement shape in details. Also because this will be model dependent also, let me say, and
Yeah.
So keep the data on the PSM models, and
we're not yet at that stage. If there are no more questions, then let's thank Lorenzo again.
Actually, it's Charlie, I don't understand. I was